In this lab, we have a star orbiting a black hole of unknown mass at the origin. However, using the mass of the star and the star's trajectory, we can actually estimate the mass of this black hole. And so if I go to my code where I start to model this out, you'll see that we first have to put in the mass of the star, the amount of time between the data points, which would be 1 day, and then you'll see that we need to use the star's momentum, and we need to find the change in its momentum in order to find the net force on the star. And then, using this net force, we will be able to use the equation for the force due to gravity on that two objects have on each other, with the gravitational constant, the star's mass, and we pretty much solve for the one variable that we won't have, which would be the mass of the black hole. And so now you may be thinking to yourself, well, okay, all we had was the star's mass and the star's trajectory. How do we get from there to the net force on the star? And what we used is Newton's second law. So because we know the mass of the star and the velocity of the star, we can find out the momentum of the star. And due to Newton's second law, which is the momentum principle, we know that the net force on an object is equivalent to the rate of change in its momentum. And so we simply can set the net force on the star equal to the change in momentum, the rate of change of its momentum. And so if we run the program, you'll see that I have these indicators that show the orange one being the net force on the object, and the pink being the parallel momentum, and the blue being the perpendicular momentum and also force. And so if I just run it one more time, you'll see that as we get closer to the object, as the star gets closer to the black hole, this net force increases, and as it gets farther, that decreases, which makes perfect sense, as we know from, again, that formula to find the force between two objects, the gravitational force between two objects. As they get closer, the force will be stronger. And so, what does this mean for us? Well, it means that since we can figure out the momentum, we know that we can figure out the mass of the black hole. And so this means that if I run it one more time here, the average mass of the black hole, so we have all these values here, if we average them up, the average mass ended up being 1.48 times 10 to the 34th. And here you'll also see the net force, the parallel force, the perpendicular force, and again, these net forces are equal due to Newton's second law. We know that these net forces are equal to the object's change in momentum over time, rate of change of momentum rather. And so if this black hole was exchanged for a different black hole, what then? What happens then? Well, we would just do the same thing. It would just be the same equations. We would do the same thing, and we would be able to find the mass again using this same exact formula and the same exact method. Obviously, the path of the star would change, but we would still be able to calculate this new mass because we would be able to see that the momentum is changing differently. The momentum would be changing differently because the forces on the object would be different. And so, yeah, thank you for coming to my lab.